The sun has been burning for 4.5 billion years. Every second, it converts 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to roughly 91 billion 1 megaton nuclear bombs detonating simultaneously. It has done this every single second since before the Earth had oceans, and it will keep doing it for another 5 billion years. We take that for granted to a degree that is genuinely staggering. What would happen if it stopped? Not in 5 billion years, not gradually, right now, completely, in this exact moment. The answer is more layered, more strange, and in some ways more hopeful than you might expect. And tracing it out reveals something remarkable about how life persists, where energy actually comes from, and what the word habitable really means at the edge of survival. Let's begin with what you would not notice immediately, because that itself is one of the stranger facts in this story. Light from the sun's surface takes about 8 minutes and 20 seconds to reach Earth. That's roughly 150 million kilometers at the speed of about 300,000 kilometers per second. So if the sun went dark at this exact moment, you would not know for 8 minutes and 20 seconds. The light already traveling toward you would complete its journey. For those final minutes, you would be basking in what is essentially a ghost signal, photons that left a star that no longer exists. This delay is not just a curiosity. It's a reminder of how disconnected we are from the present state of distant objects. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the nearest star beyond our sun, Proxima Centauri, you see it as it was 4 years ago. When you look at the Andromeda Galaxy, you're looking at light that left it 2.5 million years ago. The universe we observe is always a record of the past, not a window into the present. But for our purposes, the delay is 8 minutes and 20 seconds, and then everything changes. The moment that final wave of sunlight reaches the atmosphere and dissipates, the sky goes dark. Not the gradual darkening of sunset, not the amber transition of dusk. Instantaneous, absolute darkness across every time zone experiencing daylight. The sun doesn't set, it simply isn't there. Within seconds, the stars become visible. Every star in the sky, in both hemispheres, simultaneously present. The Milky Way, which is routinely washed out by solar glare even at night, would appear as a sharp, dense band of light. The darkness would be so complete and so total that people in cities, surrounded by artificial light, would be looking up at a sky that most of them have never actually seen. The moon would vanish. This is one of the overlooked consequences. The moon generates no light of its own. It is entirely a reflector of sunlight. Without incoming solar illumination, the moon becomes invisible, not metaphorically, but literally absent from the sky. The same is true for every planet in the solar system. Jupiter, Saturn, Venus, Mars, all of them dark. What would remain visible are the stars and galaxies, sources of their own light. The universe, minus our own sun, would suddenly be spread across the sky in a way that most humans alive today have never experienced. Now, let's talk about what happens to Earth itself. The first thing that stops is photosynthesis. This is the critical biological event, and it begins immediately. Photosynthesis is the process by which plants, algae, and certain bacteria use sunlight to convert carbon dioxide and water into glucose and oxygen. It is not just how plants grow, it is the foundation of nearly every food web on the planet. It is also the primary source of the oxygen in Earth's atmosphere. Without sunlight, photosynthesis stops. The oxygen in the atmosphere doesn't disappear immediately, there's far too much of it for that. Earth's atmosphere contains roughly 1.2 times 10 to the 18th grams of oxygen. That's a reservoir built up over billions of years of photosynthetic activity. Humans wouldn't start noticing oxygen depletion for an extremely long time. the immediate biological crisis is not suffocation. It's food. Every organism that eats plants, or eats something that eats plants, or eats something that eats something that eats plants, depends on photosynthesis at the base of its food chain. That includes almost everything on land. The agricultural systems that feed 8 billion humans depend on the ability of crops to convert sunlight into calories. Remove the sunlight, and you haven't just dimmed the fields. You've shut off the input that drives the entire system. In the first 24 hours, most people would not yet understand what had happened. Communication infrastructure would still function. Power grids, where they rely on solar panels, would begin to fail solar power accounts for roughly 5% of global electricity generation, but in some regions, it's significantly higher. In places like parts of California, Southern Europe, the Middle East, and India, grid operators would face cascading failures as solar generation dropped to zero. The psychological impact of perpetual darkness descending without warning would be severe. The portion of Earth that was experiencing daytime when the sun went dark would be the most disoriented. They would have gone from full daylight to absolute night in an instant. There would be no precedent, no frame of reference. Emergency services would be overwhelmed, not by any single physical disaster, but by the sheer scale of mass psychological distress. Temperature is where the physics becomes crucial, and also somewhat counterintuitive. Earth would not freeze instantly, not in the first day, not in the first week. The planet has enormous thermal mass. The oceans alone store enough heat to moderate global temperatures for quite some time, but the trajectory would be clear and relentless. The average surface temperature of Earth is currently about 14 degrees Celsius. That's 57 degrees Fahrenheit. This temperature is maintained primarily by two mechanisms: incoming solar radiation and the greenhouse effect in the atmosphere. Without solar input, the greenhouse effect continues to trap heat that's already present. But without new energy coming in, the total thermal budget of the atmosphere and oceans begins to decline. Within 24 hours of the sun going dark, surface temperatures would drop by approximately 15 to 20 degrees Celsius. That's a fall of about 27 to 36 degrees Fahrenheit. In most tropical and temperate regions, this would bring temperatures from comfortable to uncomfortably cold. In regions already experiencing winter, it could bring temperatures to dangerously low levels. This rate of cooling is not uniform. Oceans cool much more slowly than land because of their depth and their thermal capacity. Coastal regions would experience slower temperature drops than inland areas. Places like the interiors of continents, the heartlands of North America, Central Asia, interior Australia, would cool faster and more severely than coastal zones. The atmosphere itself acts as an insulating blanket, and it continues to function even without sunlight. The greenhouse gases, primarily water vapor, carbon dioxide, methane, and nitrous oxide, continue to trap outgoing infrared radiation. This means the cooling is gradual rather than immediate. Earth doesn't become a snowball overnight, but the direction is fixed. After 1 week without sunlight, average surface temperatures would have dropped to approximately negative 17 degrees Celsius. That's about 1 degree Fahrenheit. Most of the planet's surface, which had previously been inhabitable temperate zone, would now be experiencing conditions comparable to the deep polar winter. What's happening at this point biologically is catastrophic in the terrestrial environment. Annual plants, the vast majority of human food crops, would be dead or dying. Corn, wheat, rice, soybeans, vegetables. Almost everything in a field or garden would either have frozen or starved for energy. The only terrestrial plants surviving with any confidence at this stage would be deep-rooted perennials in warmer underground zones, some fungi, and species adapted to extreme cold. Herbivores dependent on fresh plant material would begin dying within days of losing their food source. Animals with stored body fat, hibernation physiology, or the ability to switch dietary strategies would fare better in the short term. But the food web disruption would cascade upward. Predators that depend on herbivores would find their prey vanishing. Scavengers would have a brief abundance, followed by scarcity. The oceans tell a different story, and it's one of the most important parts of this scenario. The ocean is not just a body of water. It is a vast, layered, thermally massive system that responds to temperature changes on timescales of decades and centuries, not days. The surface of the ocean would begin cooling relatively quickly. The top few meters would approach freezing temperatures within weeks. But the deep ocean, everything below a few hundred meters, would remain essentially unchanged for decades or centuries, because it's insulated by the sheer volume of water above it, and because the sun barely penetrates it anyway. The deep ocean ecosystem is fundamentally different from anything on land. It doesn't run on photosynthesis. It runs on chemosynthesis, a process by which certain bacteria oxidize inorganic compounds, like hydrogen sulfide, to produce energy. At hydrothermal vents, cold seeps, and other geologically active zones on the seafloor, entire ecosystems exist with no connection whatsoever to solar energy. Tube worms meters long, eyeless shrimp, giant clams, octopuses, and fish adapted to total darkness and crushing pressure. These ecosystems would be completely unaffected by the absence of the sun, at least for centuries or millennia. They have been unaffected by sunlight their entire evolutionary history. The sun's disappearance would not register at the sea floor of the Pacific Ocean for an extraordinarily long time. This is not a trivial observation. It reframes the question of what surviving without the sun means. It means that life, substantial, complex, diverse life, would persist on Earth regardless of what happened on the surface. After 1 month without sunlight, the situation on the surface would be severe. Surface temperatures would average around -30 degrees Celsius, which is -22 degrees Fahrenheit. The Arctic and Antarctic regions, already cold, would be in deep freeze. The temperate zones, where most of humanity lives, would be experiencing conditions colder than anything recorded in historical climatology for those regions. Ice would be spreading from the poles. The surface of the oceans in mid-latitudes would be beginning to freeze. The ice on the surface of the ocean creates a new feedback loop. It reflects any remaining heat outward, and it insulates the ocean below. So, while the ocean surface freezes, the deep water is actually somewhat protected by the ice layer above it. Plant life at this point would be reduced to extraordinary holdouts. Certain coniferous trees, species like Siberian larch, black spruce, and alpine fir, have evolved to survive temperatures that would kill most plants. Their antifreeze compounds and cellular adaptations allow them to endure prolonged deep freezes. They wouldn't be doing much growing, they wouldn't be photosynthesizing, but they wouldn't all be dead either. Seeds from annuals, meanwhile, would persist in the frozen soil. Seeds are one of evolution's most impressive inventions, metabolically dormant, protected by tough coats, viable for years or decades under the right conditions. By the 1-month mark, humanity's survival strategy would have shifted entirely to underground living and geothermal energy. Geothermal energy is the heat generated by Earth's interior. It comes from two sources: residual heat from the gravitational collapse that formed the planet about 4.5 billion years ago, and the ongoing decay of radioactive isotopes in Earth's mantle and crust, primarily uranium-238, uranium-235, thorium-232, and potassium-420. Together, these generate approximately 47 terawatts of continuous heat, roughly 47 trillion watts, flowing outward through Earth's surface. This is small compared to the roughly 170 petawatts of solar energy that normally reaches Earth's outer atmosphere. That's 170 quadrillion watts. But it is continuous. It is not dependent on the sun, and in certain geological zones, it is intense enough to sustain ecosystems. Iceland is the obvious example. Iceland sits on the mid-Atlantic ridge, a divergent tectonic plate boundary where two plates are slowly pulling apart and magma wells up from below. The island has over 130 volcanoes, roughly 600 hot springs, and geothermal systems that currently provide about 65% of Iceland's primary energy and 90% of its home heating. The ground temperature, a few meters down in Iceland, is warm enough to garden year-round, regardless of air temperature. The Yellowstone caldera in the United States, the geothermal fields of New Zealand, the volcanic zones of Japan, the Rift Valley in East Africa, all of these regions would become, essentially, the last habitable zones on the land surface of Earth. Life near geothermal sources doesn't need the sunday. The bacteria living in hot springs in Yellowstone thermophiles and hyperthermophiles survive at temperatures between 60 and 120 degrees Celsius. They metabolize sulfur compounds, iron, and other inorganic materials. They've been doing it for billions of years. For them, the presence or absence of the sun is irrelevant. Humans, obviously, are not thermophilic bacteria, but the existence of geothermal energy means that communities living near these zones could, in principle, maintain warmth, generate electricity, grow food in heated underground facilities, and sustain themselves indefinitely if they planned and organized effectively. This is not science fiction. Geothermal energy systems already exist. Iceland heats its greenhouses geothermally. Deep earth mining operations maintain habitable temperatures underground through geothermal management. The technical capacity to build insulated underground habitats fed by geothermal power using hydroponic agriculture that doesn't require sunlight is available today. Not easily, not without enormous effort, but it is within the range of human technological capability. The challenge is not primarily technological, it's logistical, political, and psychological. You would be organizing billions of people under conditions of near total collapse of surface civilization, in the dark, in plummeting temperatures, with disrupted communication and supply chains, toward a long-term survival strategy that most of them had never contemplated. The difficulty is not building a geothermal greenhouse. The difficulty is everything else. 1 year without sunlight brings Earth into territory that researchers have actually modeled with some rigor, because it resembles, in some ways, scenarios that have happened before. The most analogous real event in Earth's history is a concept called snowball Earth. Roughly 700 million years ago, and possibly again around 600 million years ago, geological evidence suggests that Earth may have been almost entirely frozen, with glaciers reaching the equator and average surface temperatures well below freezing. The mechanisms that caused snowball Earth are still debated, but the fact that life survived it and that the subsequent recovery was followed by an explosion of complex multicellular life known as the Cambrian explosion tells us something important. Even global freezing is survivable for life as a whole, even if individual species are devastated. After 1 year without sunlight, the surface temperature of Earth, according to modeling by researchers like Professor David Stevenson at the California Institute of Technology, would be approximately -40 degrees Celsius. That is also -40 degrees Fahrenheit, the point where the two scales intersect. At this temperature, most surface water is frozen solid. The atmosphere still exists, still circulates, still has its greenhouse gases. The weather systems still function, though they're profoundly changed by the absence of the primary energy input that drives them. Wind patterns emerge from temperature differentials. Without solar heating of the tropics, the massive convection cells that drive trade winds, monsoons, and much of global weather circulation would weaken significantly. The atmosphere would become more stagnant. Storms would become less frequent and less energetic. Precipitation patterns would shift drastically, though exactly how is difficult to model precisely. Below the ice, in the ocean, something interesting happens. The ice layer at the surface acts as an insulator. The deeper ocean is receiving geothermal heat from below hydrothermal vents, seafloor spreading, volcanic activity at mid-ocean ridges. The heat can't escape through the ice above as efficiently as it could escape through open water, so the deep ocean stays warmer than surface conditions would suggest. Liquid water, at varying temperatures, depending on depth and geological context, persists for centuries and potentially millennia. The oceans will not freeze solid for a very long time, not decades, perhaps not centuries. This is one of the most important facts in this scenario, because liquid water and chemical energy mean that life continues. Professor Stevenson's analysis, extended further, suggests that surface temperatures would continue declining over thousands of years, eventually approaching the temperature of deep space, roughly -270 degrees Celsius, as the residual heat of the planet radiates away. But thousands of years is a long time, long enough, potentially, for something to change. There's a scenario that cosmologists find genuinely interesting. Even if its probability is extremely low, a rogue planet picking up life and delivering it to a new stellar system. Earth, without the sun's gravity, would fly off into the galaxy. It would wander through interstellar space for potentially millions of years before encountering another star. The chance of drifting close enough to a habitable zone around another star is vanishingly small. But in a galaxy of 200 to 400 billion stars, even a very small probability attached to a very large number of opportunities is not zero. There are models that suggest a planet with a thick enough atmosphere and enough internal heat could maintain liquid water beneath a frozen surface, essentially indefinitely, not for thousands of years, but for billions of years. The atmosphere acts as an insulating blanket, trapping geothermal heat. If Earth somehow retained its atmosphere during its journey through interstellar space, which is not certain but is possible, then the conditions for microbial life near geothermal vents could persist for an extraordinarily long time. This isn't hope dressed up as science. It's an actual physical possibility that researchers have calculated. A planet with the right geochemistry, the right atmospheric composition, and the right level of internal heat could sustain microbial ecosystems indefinitely without any star at all. We might already know of such worlds. The moons Europa and Enceladus, orbiting Jupiter and Saturn respectively, are believed to have liquid water oceans beneath their icy surfaces, heated by tidal flexing from their parent planets, rather than by the Sunday. Whatever life might exist there, and researchers genuinely consider it possible, it has never needed the Sunday. Now let's set aside the hypothetical and look at what we actually know about the Sun's real future, because the Sun will not suddenly go dark, but it will change, and the timeline is worth understanding. The Sun is currently a middle-aged main sequence star classified as a G-type yellow dwarf. It has been burning for about 4.5 billion years and has roughly 5 billion years of hydrogen fuel remaining in its core. Throughout this period, it will gradually brighten. The Sun today is about 30% brighter than it was when Earth formed. This gradual increase in luminosity is one of the reasons that the early Earth's climate, despite a fainter sun, was warm enough for liquid water, a puzzle that took decades to resolve and involved understanding the different composition of the early atmosphere. As the Sun continues to brighten over the next billion years, Earth will become increasingly warm. Roughly 1 billion years from now, the increased solar luminosity will begin to make Earth's surface uncomfortably warm for complex life. Oceans will begin to evaporate more aggressively. Water vapor, a powerful greenhouse gas, will accelerate warming. This is the beginning of what climate scientists call the moist greenhouse or runaway greenhouse effect. It is the process that transformed Venus from a potentially habitable world into the hellscape it is today. A planet with surface temperatures of about 465 degrees Celsius and an atmosphere 90 times denser than Earth's, composed almost entirely of carbon dioxide. Earth faces a version of that fate eventually, though on a much longer timescale. The specific timing depends on factors like cloud feedback and atmospheric chemistry that are still being refined. But the general consensus is that Earth's surface will become uninhabitable for complex life within about 1 to 2 billion years due to increasing solar luminosity. But the dramatic phase comes later. In roughly 5 billion years, the Sun will exhaust the hydrogen fuel in its core. When this happens, the fusion process that has balanced the Sun's gravity for its entire life will falter. The core will contract. The contraction will heat the surrounding layers, igniting hydrogen fusion in a shell around the core. This shell burning releases enormous energy that pushes the outer layers of the Sun outward. The Sun will begin expanding. Over the course of roughly 1 billion years, the Sun will swell from its current diameter, about 140 million kilometers, to a red giant with a diameter perhaps 200 times larger. The surface temperature will drop from its current roughly 5,500 degrees Celsius to about 3,000 degrees Celsius, shifting the color from yellow-white to orange-red. The luminosity will increase enormously despite the lower surface temperature, simply because the surface area is so much larger. At its maximum expansion, the red giant Sun will likely engulf Mercury, Venus, and possibly Earth, though the exact fate of Earth remains uncertain because as the Sun loses mass during this expansion phase, the gravitational pull weakens and Earth's orbit may shift outward. Some models suggest Earth escapes engulfment. Others suggest it does not. The uncertainty reflects real gaps in our understanding of late-stage stellar mass loss. What's not uncertain is that Earth's surface will be incinerated well before any engulfment occurs. At red giant luminosities, Earth would receive energy equivalent to about 5,000 times what it receives today. Surface temperatures would reach several thousand degrees Celsius. Oceans would have evaporated billions of years earlier. After the red giant phase, in roughly 5 to 7 billion years, the Sun will shed its outer layers in an event called a planetary nebula, a beautiful but misleading name since it has nothing to do with planets. The ejected shell of gas expands outward at speeds of tens of kilometers per second, glowing in ultraviolet radiation from the hot core left behind. This process takes thousands of years. What remains at the center is a white dwarf, a stellar remnant, roughly the size of Earth, but with a mass about half the current Sun's mass, composed primarily of carbon and oxygen, and no longer undergoing fusion. A white dwarf simply cools, slowly, over billions of years. It radiates its stored thermal energy into space, dimming gradually from white to yellow to orange to red to infrared, eventually becoming a cold, dark object called a black dwarf. The time required for a white dwarf to cool to a black dwarf is longer than the current age of the universe. So there are no black dwarfs yet. Every white dwarf that has ever formed is still glowing. The white dwarf Sun, surrounded by whatever remains of the outer solar system, perhaps Jupiter, Saturn, some asteroids, some icy remnants, will persist for hundreds of billions of years, slowly cooling in the dark. This is the real future of our star. Not sudden darkness, not a switch that gets flipped, a long, slow unraveling over timescales that are difficult to intuitively grasp. But the thought experiment about sudden darkness is not without value. It illuminates something that is easy to overlook in ordinary life: the degree to which surface life on Earth is a thin, solar-powered film on a planet that has its own internal energy budget, its own heat, its own chemistry, and its own ecosystems that predate and will outlast the particular configuration we call the biosphere. The deep ocean hydrothermal vent communities were discovered in 1977 by a team of researchers aboard the submersible Alvin near the Galapagos Rift in the Pacific Ocean. The discovery is often described as revolutionary, and the word is appropriate. Before 1977, the assumption was that all food webs ultimately traced back to photosynthesis. The vent communities shattered that assumption. Here were thriving ecosystems, tube worms nearly 2 meters long, white crabs, clams, fish, shrimp, in a place where no sunlight had ever reached, running entirely on chemical energy extracted from the superheated, mineral-rich water emerging from the seafloor. The organisms at the base of these food webs, the chemosynthetic bacteria, perform reactions that are chemically distinct from photosynthesis, but functionally analogous. They extract energy from oxidizing compounds like hydrogen sulfide, methane, ferrous iron, and ammonia. They use this energy to fix carbon dioxide into organic molecules, building the base of a food chain that supports everything living above them. They are metabolically independent of the sunday. Since 1977, dozens of hydrothermal vent systems have been identified across the world's oceans. Cold seeps areas where hydrocarbon-rich fluids percolate up from the seafloor have been found to support their own chemosynthetic ecosystems. Some of these ecosystems are among the most productive on Earth in terms of biomass per unit area. The astrobiological implications of vent communities are immense, and this is where the thought experiment intersects with some of the most active research in space science. If life can exist entirely without sunlight on Earth, then solar energy is not a requirement for life. It's one pathway, a convenient, abundant, efficient pathway that happens to dominate the surface of our planet, but not the only one. Enceladus, the moon of Saturn, was identified by the Cassini spacecraft as a place with active hydrothermal venting. The spacecraft flew through geysers, erupting from the moon's south pole, and detected water vapor, organic molecules, molecular hydrogen, silica nanoparticles, and carbon dioxide. The presence of molecular hydrogen is particularly significant. It indicates an ongoing chemical reaction between hot water and rock, the same reaction that drives chemosynthesis at Earth's hydrothermal vents. The Cassini team published their analysis in 2017, and the conclusion was direct. Enceladus has the chemical ingredients for chemosynthetic life. Europa, orbiting Jupiter, has a surface of pure water ice covering what is believed to be a subsurface ocean roughly 100 kilometers deep. The total volume of water in Europa's ocean is estimated to exceed the total volume of all liquid water on Earth. Tidal flexing from Jupiter's gravity heats Europa's interior, maintaining the liquid ocean. Europa has long been considered one of the prime candidates for extraterrestrial life in the solar system, and missions like the Europa Clipper, launched in October 2024, are designed specifically to investigate its potential habitability. The question of whether life exists in these places is genuinely open. Nobody knows. But the question is serious enough that NASA, the European Space Agency, and several national agencies are investing significant resources in finding out. The premise of the investigation is exactly what the thought experiment about the missing sun leads you to. Life may not need a star. Back on Earth, and back to the scenario we've been tracing, there's a final element that deserves attention: the long timescale. The scenario begins with immediate, catastrophic consequences for surface life, but zoom out and the picture is more complex. The deep ocean persists, the geothermal zones persist. Microbial life in the crust persists, and this point deserves emphasis, because subsurface microbial life on Earth may represent a larger total biomass than all surface life combined. Researchers studying deep subsurface environments have found living bacteria at depths exceeding 5 kilometers below the surface, in rock formations hundreds of millions of years old, surviving on hydrogen generated by the reaction between water and iron-containing minerals. These organisms are metabolically slow. Some of them may divide once every 1,000 years, but they are alive. They are metabolizing. They are adapting. They are, in some sense, indifferent to what happens on the surface. A study published in 2019 by an international consortium called the Deep Carbon Observatory estimated that life in Earth's crust extends to depths of at least 5 kilometers and possibly deeper, with a total biomass roughly equivalent to that of all life on the surface. The organisms found at these depths include bacteria and archaea, adapted to pressures of hundreds of atmospheres, temperatures of up to about 120 degrees Celsius, and chemical environments utterly different from anything on the surface. Remove the sun, and these organisms continue. Remove the oceans, and they continue. They are the baseline of life on Earth, the constant, the thing that persists when everything else fails. This has historical grounding. Earth has been through 5 major mass extinction events. The most severe was the Permian-Triassic extinction event, about 252 million years ago, which eliminated roughly 96% of all marine species and 70% of terrestrial vertebrate species. The cause was a combination of massive volcanic activity, ocean acidification, and anoxic conditions. It was the closest thing Earth has experienced to a biological near-death event. Life survived, not because of any particular resilience at the top of the food chain. The dominant species were wiped out. Life survived because it persisted in the margins in deep water refugia, in isolated geothermal zones, in subsurface environments, in whatever pockets of stability existed through the catastrophe. The recovery took millions of years, but it happened. The question the thought experiment about sudden darkness actually asks is not, would life survive? Life would survive. The question is, would humans survive? And the honest answer is, some might. Not billions, not hundreds of millions, perhaps thousands, perhaps tens of thousands, perhaps more if global coordination happened quickly and effectively, gathered near geothermal sources, living underground, growing food in sealed, artificially lit, hydroponically managed facilities, relying on nuclear power and geothermal energy rather than solar power. Over generations, adapting to an environment that receives no input from the sunday. The technology to do this already exists in partial form. Nuclear reactors generate electricity without sunlight. Hydroponic agriculture under artificial lighting works. Underground habitats have been designed and tested. The International Space Station demonstrates that closed-loop life support, recycling water, managing atmosphere, growing food is technically achievable. None of these are simple. None of them are cheap, but they are real. The scenario is a thought experiment that reveals the actual foundations of human civilization, our dependence on a single star, and the alternative foundations that would have to be built in its absence. It's a useful thought experiment, not because the sun is going to suddenly disappear, it is not, but because it clarifies what we depend on and what we might depend on instead. The deeper point is this: the sun is not the only source of energy capable of sustaining life. It is the most convenient, most abundant, and most historically dominant source for surface life on Earth. But Earth has its own internal energy. The galaxy has hundreds of billions of stars, and many of them have planets. And we now know that some of those planets may harbour life that never knew a star at all. The sun will continue to shine for another 5 billion years. It will brighten gradually. It will eventually expand into a red giant, engulf the inner planets, shed its outer layers, and collapse into a slowly cooling white dwarf. That is not sudden darkness. That is a slow conclusion to a story that started 4.5 billion years ago. In the meantime, the question of what life actually requires solar energy, or simply energy, is being answered in real time by researchers drilling into the deep crust, sending spacecraft to ocean moons, and designing missions to search for biosignatures on worlds that may never have seen a sunrise. The sun going dark is a thought experiment. The answer it leads to is real science. Let's go back to the first minutes and slow everything down, because there's more happening in that initial window than the sudden darkness suggests. When the sun's light stops reaching Earth, the effects don't arrive all at once. They arrive in sequence, governed by the different speeds at which different things travel. Light itself arrives first, or rather, stops arriving at the speed of 300,000 kilometers per second, but the sun sends more than light. The solar wind is a constant stream of charged particles, mostly electrons and protons, that flows outward from the Sun at speeds between 300 and 800 kilometers per second. It takes the solar wind anywhere from 1 to 4 days to reach Earth. This wind is not strong enough to feel, it's not strong enough to push a leaf, but it is responsible for shaping Earth's magnetosphere, carving it into an asymmetric teardrop shape with a long tail stretching away from the sunday. When the solar wind stops, the magnetosphere would begin to relax into a more spherical shape. The auroras, the northern and southern lights, are produced by charged particles from the solar wind interacting with Earth's magnetic field and upper atmosphere. They would fade as the solar wind supply depleted. Bright displays might appear in the final days as residual particles completed their journey. Then silence, magnetically speaking. But something more subtle happens to the ionosphere. The layer of the atmosphere between about 60 and 1,000 kilometers altitude that contains ionized particles maintained by solar radiation. The ionosphere is what makes long-distance radio communication possible. High-frequency radio waves bounce off the ionosphere and can travel thousands of kilometers beyond the horizon. Without solar ionization, the ionosphere's ion density would begin to fall. Some of its layers, particularly the higher F layer, would deplete faster than others. Long-distance radio communications would become unreliable within days, then unavailable. In a crisis scenario where infrastructure is already failing, this loss of communication range would be a serious blow to coordination. The disappearance of the solar wind also removes the heliosphere, the bubble of solar particles that extends well beyond the orbit of Neptune and creates a partial shield against galactic cosmic rays. With the heliosphere gone, the flux of high-energy cosmic ray particles at Earth's surface would gradually increase. Not catastrophically, Earth's atmosphere and magnetic field still provide significant shielding, but over decades, the increased cosmic ray exposure would elevate radiation doses, particularly at high altitudes and polar regions. The stratospheric ozone layer, which absorbs ultraviolet radiation from the sun, would remain in place. In fact, without incoming ultraviolet radiation to create and maintain ozone through photochemical reactions, the ozone layer would gradually thin over decades as ozone molecules were destroyed faster than they were created. But on the timescale of days and weeks, the ozone layer would still be intact and still shielding the surface from ultraviolet light. Not that ultraviolet light would be a concern without a functioning star to generate it. The atmosphere itself, let's be specific about it, has a mass of about 5 times 10 to the 18th kilograms. That's 5 quadrillion metric tons. It has enormous thermal inertia. In the first 24 hours, the troposphere, the lowest layer where weather happens, would begin to cool at its upper boundaries, but the surface level air would still retain much of its heat. The temperature gradient that drives convection, thunderstorms, and weather systems would still exist. Weather would not immediately stop, but it would change in character. The absence of solar heating over land and ocean surfaces would weaken the temperature gradients that drive circulation. The tropics, which normally receive far more solar energy per unit area than the poles, would stop being special. The equator to pole temperature gradient that drives the general atmospheric circulation, the jet streams, the Hadley cells, the Ferrel cells, would begin to weaken and ultimately fail. Global wind patterns would shift. Precipitation patterns, which depend critically on temperature-driven evaporation and atmospheric circulation, would become unpredictable and eventually would largely cease as temperatures dropped below the frost point everywhere. The first rains after the sun went dark would be strange. They would fall from a sky that showed stars at all hours. They would be colder than seasonal norms. As temperatures plummeted in the weeks that followed, rain would transition to snow at lower and lower elevations until precipitation everywhere fell as ice or snow. The snowfall itself would create a powerful feedback mechanism. Snow reflects sunlight. Under normal conditions, the high albedo of snow-covered ground helps cool the poles and moderate the global temperature budget. Without sunlight to reflect, the reflectivity of snow doesn't directly matter for incoming energy. There is none. But the white surface would radiate infrared heat slightly differently than bare ground, and more importantly, the insulating properties of snow would protect underlying soil from the very deepest temperatures. Beneath a meter of snow, the ground temperature remains significantly warmer than the air above. This is why small mammals can survive polar winters in subnivean under-snow environments, finding insulation in the snowpack against air temperatures that would otherwise kill them. This matters because soil is not just dirt. It is a complex ecosystem. A single teaspoon of healthy soil contains roughly 1 billion bacteria, thousands of fungi, and an array of other organisms. These soil microbes are essential for nutrient cycling, decomposition, and ultimately the regeneration of plant life. Many of them are cold tolerant or cold dormant. Freeze the soil and they slow down or enter suspended states. Many would not die. In the insulated environment beneath snowpack, soil microbial communities might persist in dormant form for remarkably long periods. Seeds, as mentioned earlier, are even more robust. The permafrost regions of Siberia have yielded viable seeds of Silene stenophila, a flowering plant that were estimated to be about 32,000 years old. They were extracted from permafrost deposits, germinated in a laboratory, and grew into full plants. This remarkable discovery was published in 2012 and demonstrated that seeds can remain viable at sub-freezing temperatures for timescales that dwarf the entire span of recorded human history. If Earth froze and then somehow recovered, if the sun came back or a replacement heat source was established, the seeds in the frozen soil could potentially germinate and begin rebuilding terrestrial plant communities. This is not a plan. It is not a hopeful prediction. It is an observation about biological resilience that the fossil record and modern experiments both support. The thought experiment about sudden solar darkness is, in part, a stress test on the concept of biological irreversibility. At what point does the damage become permanent? The answer, surprisingly, is later than intuition suggests. 1 week in, some countries would begin executing emergency protocols that already exist. The United States, for example, has continuity of government plans, nuclear-powered submarines, and military installations in geologically stable underground facilities. Nuclear-powered vessels, submarines, and aircraft carriers would be among the most functional pieces of infrastructure on Earth, because their energy source is completely independent of the sunday. A nuclear submarine can remain submerged and fully operational for roughly 3 months on a single fuel load. In the scenario of sudden solar darkness, the world's nuclear-powered vessels would be among the few functional, self-contained, independently powered facilities available. Russia has extensive experience with Arctic survival and has military installations in some of the coldest and most geologically active regions on Earth. Iceland's geothermal infrastructure would make it one of the most immediately adaptable locations on the planet. It already heats its buildings and grows food in geothermally heated greenhouses year-round. Switzerland's extensive network of bunkers and civil defence infrastructure would provide protected underground living space for a significant portion of its population. None of these resources scale to 8 billion people. The honest assessment of human population survival under prolonged solar darkness is that the carrying capacity of Earth without solar energy would be a tiny fraction of the current population. Exactly how tiny depends on assumptions about how quickly geothermal infrastructure could be scaled, how efficiently nuclear energy could be repurposed, and how effectively global coordination could be maintained under conditions of extreme stress. Researchers who have modelled what they call global catastrophic risk scenarios, a category that includes nuclear winter, supervolcanic eruptions, and asteroid impacts, have noted that one of the consistent findings across models is that population decline does not mean extinction. Even in the most severe scenarios that have been modelled, small pockets of survival remain. The question of how many, and under what conditions, is one that catastrophe risk researchers take seriously as a policy-relevant question rather than a purely hypothetical one. The reason this matters is that some of the scenarios we should be preparing for large-scale nuclear exchanges, supervolcanic eruptions, major asteroid impacts would produce effects somewhat analogous to the solar darkness scenario. The so-called nuclear winter concept, developed by researchers including Carl Sagan and colleagues in the 1980s, described how a large-scale nuclear exchange could inject enough soot and aerosols into the stratosphere to block sunlight for months or years. The estimated temperature drops and agricultural collapses in that scenario are comparable in some ways to the early stages of our thought experiment. The Toba catastrophe, approximately 74,000 years ago, provides a real-world parallel. The Toba supervolcano in what is now Sumatra, Indonesia, erupted with a force estimated at roughly 2,800 cubic kilometers of material ejected. It was the largest volcanic eruption in the last 2 million years. The eruption is hypothesized to have caused a volcanic winter lasting 6 to 10 years, with surface temperatures dropping by several degrees globally. Genetic evidence has been interpreted to suggest that the human population may have been reduced to perhaps 10,000 to 30,000 individuals globally, a population bottleneck that would have represented near extinction. The interpretation of the Toba bottleneck is contested. Some researchers question whether the genetic evidence actually reflects a population crash or simply normal patterns of human migration. But the event itself is not contested. Toba erupted. The ash layers are globally distributed. The aerosol injection into the stratosphere almost certainly caused regional, if not global, cooling. And humanity still at a technological level roughly equivalent to early stone tools survived. This is the historical grounding for the claim that small groups of humans could survive even extreme global disruptions. The conditions would be radically different from those of Toba 74,000 years ago, both in severity and in our technological capacity to respond. But the precedent of biological and social survival under extreme environmental stress is documented. Now consider what happens to the atmosphere over longer timescales. The atmosphere is held to Earth by gravity. It is not going anywhere on human timescales, but its composition can change. Currently, the atmosphere is about 78% nitrogen, 21% oxygen, roughly 1% argon, and small amounts of carbon dioxide, water vapor, and trace gases. The oxygen is maintained by photosynthesis. Without photosynthesis, oxygen would still be available for a very long time because the reservoir is enormous. But the renewal mechanism would be gone. Oxygen does eventually combine with other elements. It oxidizes iron, forming rust. It combines with organic molecules during decomposition. Over geological timescales, oxygen disappears from atmospheres that lack a photosynthetic source. Mars's atmosphere is less than 1% oxygen, and what little exists is maintained by photochemical breakdown of carbon dioxide and water in the upper atmosphere, rather than by any biological process. For humans, the relevant question is not whether oxygen would run out in the first year without the Sunday. It would not. The relevant question is whether carbon dioxide would build up to dangerous levels as plants stopped absorbing it, industrial activity continued, and organic matter decomposed without the normal carbon cycle functioning. In the short term, the first month's carbon dioxide buildup would not be a significant factor. But over years, the balance of gases in the atmosphere would shift. The carbon cycle is normally a balance between sources of carbon dioxide, volcanic emissions, decomposition, respiration, combustion and sinks, photosynthesis, ocean absorption, and the formation of carbonate minerals. Without photosynthesis, the primary biological carbon sink disappears. The oceans would continue absorbing carbon dioxide, but at a reduced rate as surface waters cooled and eventually froze. The long-term trajectory would be toward a carbon dioxide-richer atmosphere, which would actually slow the surface cooling somewhat through enhanced greenhouse effect, but would make the air increasingly difficult to breathe in enclosed spaces. This matters particularly for underground survival scenarios, where ventilation and air quality management would be critical engineering challenges. You can't simply seal a human habitat underground and expect the air to remain breathable indefinitely. You need to remove carbon dioxide and add oxygen. In a world with nuclear power and technological infrastructure, this is solvable with chemical scrubbers, electrolyzers, and carefully managed plant growth under artificial lighting. But it requires intentional design and maintenance. The subject of artificial lighting leads directly to the technology of plant growth without sunlight, which is not a hypothetical. It exists today at commercial scale. Vertical farming is the practice of growing crops in stacked layers under artificial lighting, often using LED systems designed to produce the specific wavelengths most useful for photosynthesis. LEDs tuned to red wavelengths around 660 nanometers and blue wavelengths around 450 nanometers are most efficient for plant growth because they target the absorption peaks of chlorophyll, the photosynthetic pigment. Modern vertical farms in Japan, the United States, the Netherlands, and Singapore are producing significant quantities of leafy greens, herbs, and some fruits entirely without sunlight. The energy requirements are substantial. Current vertical farms use somewhere between 200 and 500 kilowatt-hours of electricity per kilogram of leafy greens produced, compared to roughly 1 to 5 kilowatt-hours for field-grown crops. That's a factor of 100 to 500 more energy-intensive. But in a scenario where the energy source is nuclear or geothermal sources that are not dependent on the sun, the absolute cost of energy is less relevant than its availability. A 1 gigawatt nuclear power plant, operating continuously, generates roughly 8.5 billion kilowatt-hours per year. If we generously assume 300 kilowatt-hours per kilogram of food produced, that's about 28 million kilograms of food per year from a single nuclear plant dedicated entirely to vertical farming. A moderately active person needs roughly 2,000 calories per day, which corresponds to roughly 500 to 700 grams of food per day, depending on caloric density. 28 million kilograms of food per year supports roughly 100,000 people per nuclear reactor dedicated to food production. There are about 440 commercial nuclear reactors currently operating in the world, with a total capacity of roughly 390 gigawatts. If those were repurposed entirely to food production, an absurd simplification, but illustrative, they could feed roughly 40 million people indefinitely. That's about 0.5% of the current human population. This back-of-envelope calculation illustrates both the possibility and the limitation. Technologically, nuclear-powered food production is real. At current nuclear capacity, it could sustain a small remnant population. Scaling nuclear capacity dramatically would require enormous resources and time, both of which would be in critically short supply during a sudden solar crisis. The realistic survival scenario for a technologically advanced civilization facing sudden solar darkness is not a comfortable transition to underground nuclear cities. It is a triage situation in which existing infrastructure is repurposed as quickly as possible. Certain populations near geothermal resources have significant advantages, and the carrying capacity of Earth without solar input would be established over decades of painful adaptation at a population level far below current numbers. There's a more abstract but important question here as well. If a small number of humans survived over a very long timescale, centuries or millennia, what would happen to their civilization? This is not a new question. Human civilization has been interrupted before. The Bronze Age collapse, around 1200 BCE, disrupted nearly every major civilization in the Eastern Mediterranean within a period of a few decades. Literacy disappeared in some regions. Long-distance trade networks collapsed. Population centers were abandoned. The recovery took centuries. Rome's collapse in the Western Empire set off a period of reduced agricultural productivity, urban abandonment, and population decline that persisted for several hundred years before recovery in some regions. These historical disruptions were severe. They were not extinction events. The knowledge, agricultural techniques, and social structures that enabled recovery survived in fragmented form through the disruptions. A group of survivors in a geothermal zone, preserving seeds, maintaining a nuclear reactor, growing food under artificial lighting, and passing knowledge through generations. They would face challenges that dwarf anything in human history. But they would not be starting from scratch. They would be starting from the technological and scientific knowledge base accumulated over the entire history of human civilization. Whether that would be enough is genuinely uncertain. The history of isolated populations on islands, in remote regions, in extreme environments, suggests that the minimum viable population for long-term survival of a complex society is far higher than the minimum viable population for biological survival. You need enough people to maintain the division of labor required to operate nuclear reactors, manage water systems, grow food, care for the sick, educate children, and maintain the social cohesion that prevents conflict from consuming the community's resources. Estimates of this minimum viable civilization vary widely, but most researchers who think about the question put it at thousands to tens of thousands of people per community, with multiple communities in contact with each other. This brings us back to the geothermal zones. Iceland, with a current population of about 370,000 people, would be one of the best positioned large communities on Earth. The country already generates about 30% of its electricity from geothermal and an additional 70% from hydropower. It grows significant quantities of food in geothermally heated greenhouses. It is an island which provides natural defense, and it has a well-educated, technically sophisticated population familiar with operating in extreme climates. The question of whether Iceland could scale its geothermal infrastructure fast enough to sustain its current population indefinitely without solar input is complex. The country currently uses its geothermal energy primarily for heating and some electricity. Converting an entire food supply to geothermally heated indoor agriculture would require massive infrastructure investment. But the geothermal resource is there, it is substantial, and the technical expertise exists. New Zealand, similarly, has significant geothermal resources and a relatively small population of about 5 million people on a resource-rich island group. The Philippines, Indonesia, Kenya, Ethiopia, and several other countries with active volcanic systems would be candidates as regional survival centers. The scenario raises a profound question about geopolitical realities. In a world where survival depends on proximity to geothermal resources, the political map of the world is irrelevant. What matters is geology. The countries and communities that would have the greatest long-term survival potential are those that happen to sit on active volcanic zones which bear no relationship whatsoever to current economic or political power. The most powerful nations on Earth, in terms of current military and economic strength, the United States, China, Russia, have geothermal resources but not uniformly distributed ones. Parts of them would survive, parts would not. The ethics of such a scenario, who gets access to the limited geothermal survival zones, who gets to enter the underground facilities, who gets to live, is a question that serious thinkers in the catastrophic risk field have engaged with. Because it's not purely hypothetical. The same triage questions arise, at smaller scale, in scenarios of nuclear winter, supervolcanic eruption, and large asteroid impact. These scenarios are real enough that they inform actual policy discussions. But let's return to the physics. because there's one more dimension of the scenario that hasn't been fully explored: what happens to the rest of the solar system. The solar system is not just the Sun and Earth. It contains 7 other planets, dozens of moons, hundreds of thousands of asteroids, countless comets, and the vast, sparse medium of the heliosphere. The Sun's gravity holds all of these objects in their orbits. It holds them through gravitational attraction alone, which does not require the Sun to be luminous. A dark sun of the same mass would still hold the solar system together. This is an important point. The thought experiment usually assumes that the Sun going out means losing both its light and its gravitational influence. But in physical reality, these are separable. A cold, dark sun would still have the same mass, still exert the same gravity. The planets would continue in their orbits. Only if the Sun somehow lost mass rapidly, which is not how stellar evolution works, would the orbital dynamics change. If we imagine the Sun somehow losing its gravitational influence simultaneously with losing its light, a physically unrealistic but dramatically useful scenario, then the planets would indeed scatter. Objects in orbit don't simply stop, they have velocity. Earth is currently moving at about 29.8 kilometers per second relative to the Sunday. The Sun's gravity is what bends Earth's path into an orbit rather than a straight line. Remove the gravity, and Earth continues in the direction it was heading at the moment the gravity disappeared. Depending on when in its orbit Earth lost the Sun's gravity, it would travel in a straight line at roughly 29.8 kilometers per second in whichever direction it happened to be heading. In 1 year, it would travel roughly 940 million kilometers. In 10 years, roughly 9 billion kilometers, the approximate distance to Saturn's orbit. In 100 years, it would be at roughly 90 billion kilometers, well into the outer reaches of the solar system. The temperature would keep dropping during this journey. At the distance of Saturn, the solar radiation received from distant stars, plus the cosmic microwave background radiation, the remnant heat of the Big Bang, would maintain the temperature at roughly negative 269 degrees Celsius, just a few degrees above absolute zero in the absence of any internal heating. Earth's surface would reach such temperatures only after thousands of years of cooling because of the insulating atmosphere and the internal heat. But the trajectory would be toward those temperatures unless the internal heating was sufficient to maintain otherwise. At some point, astronomically speaking, a rogue Earth could encounter another star. The average distance between stars in our region of the Milky Way is roughly 4 to 5 light years. At Earth's orbital velocity of about 30 kilometers per second, it would take approximately 42,000 years to travel 1 light year. So the average time to reach another star would be roughly 170,000 to 200,000 years. The Milky Way contains an estimated 2 to 400 billion stars. The total number of rogue planets, planets not gravitationally bound to any star, is estimated to be enormous. A 2021 study using gravitational microlensing data from the Microlensing Observations in Astrophysics Survey, known as MOA, estimated that there could be roughly 2 rogue Jupiter mass planets for every main sequence star in the galaxy, suggesting a total number in the hundreds of billions. Earth mass rogue planets may be even more numerous. We have found rogue planets. They have been detected through gravitational microlensing, the way their gravity briefly focuses light from background stars. They are real. Some of them may have warm subsurface oceans maintained by radioactive decay of internal elements. Some of them may harbor microbial life. This is a genuine scientific possibility, not a fantasy. The first candidate rogue planet detected with any certainty was announced in 2012 from data collected by the MOA collaboration and the optical gravitational lensing experiment known as OGLE. These surveys systematically monitor millions of stars for the brief brightness fluctuations that indicate a gravitational lens passing in front of the star. The events have timescales of hours to days, consistent with planetary mass objects, rather than the weeks to months timescales of stellar mass lenses. Over the subsequent decade, multiple more candidates have been identified. In 2023, NASA's James Webb Space Telescope identified a number of free-floating planetary mass objects in the Orion Nebula, a star-forming region about 1,344 light-years from Earth. These objects, nicknamed JUMBOs, Jupiter Mass Binary Objects, appeared to be free-floating planets, some of them in pairs, not bound to any star. Their existence challenged existing models of planet formation, because the standard mechanisms for forming planets require a host star to provide the material and gravitational framework. How planetary mass objects form without a star is a question that has not yet been fully resolved. This is the frontier of our understanding. The solar system's fate, the distribution of rogue planets, the potential for life without a star. These are questions that have gone from philosophy to active science in the past few decades. The James Webb Space Telescope, the Nancy Grace Roman Space Telescope scheduled for launch in the mid-2020s, and future missions are expected to significantly improve our census of free-floating planetary mass objects and their properties. The thought experiment about the sun going dark ultimately leads here, to the recognition that our solar system is one configuration of matter and energy among countless others, that life's relationship to stars is not one of absolute dependence, and that the universe is far more generous with the conditions for life than the clean, sunlit surface of one inhabited planet might suggest. None of this diminishes what the sun means to us. The sun is not merely a heat source. It is the reason Earth has an oxygen atmosphere, because the evolution of photosynthetic life was driven by solar energy over billions of years. It is the reason Earth has liquid water at the surface, because solar heating balanced against greenhouse warming has maintained temperatures in the narrow range compatible with surface liquid water for most of Earth's history. It is the reason complex multicellular life evolved on land, because the existence of land plants oxygenated the atmosphere and moderated the carbon cycle in ways that enabled terrestrial habitation. The sun is deeply written into the biology of every organism living on Earth's surface. The 24-hour circadian rhythm that governs human sleep, metabolism, and hormone regulation is an adaptation to the rotation of Earth relative to the Sunday. The seasonal behavior of plants, animals, and ecosystems is calibrated to the annual variation in solar angle. The color vision of many animals, including humans, evolved to function in sunlight. The chemistry of vitamin D in human skin involves photons from the sun triggering the synthesis of a molecule essential for calcium metabolism, immune function, and dozens of other biological processes. We are, in a very real sense, solar-powered organisms. Our evolution was shaped by the sun's presence. Our biology depends on it in ways that go far beyond the simple fact of temperature. But the thought experiment reveals that we are also something else. We are problem solvers. We are tool builders. We are organisms that have, in the span of a few thousand years, learned to manipulate energy sources that have nothing to do with the sun, nuclear fission, geothermal heat, chemical energy stored in batteries. We have built enclosed habitats in Antarctica, in submarines, on the International Space Station. We have grown food under artificial lights. We have designed life support systems. These capabilities are new in evolutionary terms. They did not exist 100,000 years ago. They barely existed 500 years ago. And they are accelerating. The question of whether humanity could survive the loss of the sun is therefore not a fixed answer. It is a function of when. Asked today, the honest answer is that a small fraction of the human population could survive indefinitely, at enormous cost, and through extraordinary effort, near geothermal resources and using nuclear energy. Asked in 100 years, assuming continued development of technology, the answer might be significantly different. The technology for large-scale underground agriculture, advanced nuclear systems, closed-loop life support, and interplanetary survival is developing in real time. Each of those capabilities moves the needle. The question of whether we should care about this scenario, whether it deserves investment and planning, has been seriously considered by researchers in catastrophic risk. The argument for caring about low-probability, high-consequence events is well established in risk theory. The expected harm of an event is the probability of the event multiplied by the magnitude of the harm. Even very small probabilities multiplied by existential consequences produce non-trivial expected harms. The argument for caring specifically about sudden solar darkness is weaker than for other catastrophic risks, because the physical mechanism for sudden solar darkness does not exist. Stars do not simply turn off. They can be affected by unusual stellar activity, solar flares, coronal mass ejections, but nothing on a timescale faster than millions of years. The value of the thought experiment is not preparedness for solar darkness specifically. It is illumination of what civilization actually depends on and what the alternatives are. Every serious analysis of existential risk emphasizes a common theme. Civilization's fragility is not primarily physical. Earth's atmosphere, crust, and biosphere are physically robust. They have survived asteroid impacts, supervolcanic eruptions, global ice ages, and the gradual brightening of the sun over billions of years. What is fragile is the thin layer of human organization, the agricultural systems, the trade networks, the energy infrastructure, the political institutions that allows 8 billion people to live on a planet that can sustainably support a far smaller number under pre-technological conditions. Understanding what drives that fragility, solar dependence being one clear example, is practically useful in ways that go beyond the imaginary scenario. Global catastrophes that actually reduce solar input, like supervolcanic eruptions and nuclear winter, are real risks that share many features with the thought experiment. The agricultural vulnerability that appears immediately in the thought experiment is the same vulnerability that makes nuclear winter scenarios so catastrophic. It's not the cold or the darkness directly that kills billions. It's the collapse of the agricultural systems that feed them. The researchers who study these scenarios, people like the Global Catastrophic Risk Institute, the Future of Humanity Institute at Oxford before its closure in 2024, and the Centre for the Study of Existential Risk at Cambridge, have found consistent overlap between the most catastrophic plausible risks and the vulnerabilities identified by thought experiments like the one we've been exploring. The sun is stable. It will continue to shine for another 5 billion years, brightening gradually. It will not suddenly go dark, but understanding what would happen if it did is not wasted effort. It is a way of seeing clearly what we depend on, what is robust and what is fragile, where the foundations actually are and where we only imagined them to be. The stars remain visible in the thought experiment's dark sky. They have always been there, behind the daylight. The universe is not sun-shaped. It is full of energy, in forms we are still learning to recognize and use. That remains one of the most productive scientific questions of our time. Not just how to use the sun's energy more effectively, but how to understand and eventually access the other forms of energy available throughout a universe that is, it turns out, far more hospitable to life than it first appears. What we don't yet know is where else life has found those other energy sources. We have found chemosynthetic ecosystems at the bottom of our own ocean. We have found evidence for subsurface liquid water on Europa and Enceladus. We have found possible biosignature chemistry on Enceladus that is directly analogous to life-supporting chemistry at Earth's hydrothermal vents. We have not yet found life beyond Earth. The search for that life and the understanding of what it would require is ongoing. The James Webb Space Telescope is analyzing the atmospheres of exoplanets orbiting other stars, looking for chemical signatures that might indicate biological activity. The Dragonfly mission is heading to Titan, Saturn's largest moon, with a thick nitrogen atmosphere and liquid methane lakes to assess its chemistry. Europa Clipper is on its way to the Jovian system to measure the composition and habitability of Europa's subsurface ocean. These missions were designed around a set of questions that begins with the recognition that life on Earth doesn't uniformly require the Sunday, that there are ecosystems on this planet that have been running independently of solar energy for billions of years, that the conditions for life, as we understand them, liquid water, chemical energy, organic chemistry, time, are not uniquely provided by stars. The thought experiment about a dark sun takes you there, from sudden darkness to the deep ocean, from the deep ocean to Enceladus, from Enceladus to the broad question of where else in the universe these conditions exist. The sun will keep shining, we will keep looking. And the answers to what life needs, where it can exist, and how it persists through catastrophe are still being written by researchers working at the intersection of planetary science, astrobiology, and our ever-expanding understanding of what this universe can sustain. Let's go back even further and ask a question that the thought experiment implicitly raises but rarely gets asked directly. Why does the sun produce so much energy in the first place, and why does it produce exactly the right kind? The sun emits about 3.8 times 10 to the 26th watts of power, written out. That's roughly 380 septillion watts. Every second, it converts roughly 600 million metric tons of hydrogen into 596 million metric tons of helium, with the difference about 4 million metric tons converted into pure energy via Einstein's most famous equation. The energy per second released by this process is difficult to put in human terms. It is equivalent to the detonation of roughly 91 billion 1 megaton nuclear warheads every second. Without interruption, for 4.5 billion years, with roughly 5 billion more years remaining, this energy production is not frantic or explosive. It is, in the context of stars, actually quite modest. The sun has a power density energy produced per kilogram of mass of about 276 microwatts per kilogram. That's less than the specific metabolic rate of a resting human body, which produces roughly about 1 watt per kilogram. The sun produces energy at a rate roughly 4,000 times lower per unit mass than a resting human does. What makes the sun so powerful overall is not the efficiency of its fusion reactions per kilogram, it's the sheer quantity of mass involved. This low specific power is what makes the sun stable over billions of years. Stars that burn faster, hotter, and brighter, the massive O-type and B-type stars, exhaust their fuel in millions of years rather than billions. A star 10 times the sun's mass burns through its fuel in roughly 20 to 30 million years. Life on Earth took hundreds of millions of years to progress from single-celled organisms to complex multicellular life. A star like the sun, with its slow, steady energy output over billions of years, is what gave life enough time to evolve from chemistry to complexity. This is part of what astrobiologists call the habitability factors for a stellar system. Not just having the right temperature for liquid water, that's the famous habitable zone concept, but having the right type of star that remains stable long enough for life to evolve. Too hot and massive, and the star dies before complex life can develop. Too cool and dim, and the habitable zone is close enough to the star that tidal locking, where one face of the planet always faces the star, becomes a serious problem. Too variable in its energy output, and ultraviolet flares sterilize the surface. The sun sits in a remarkably good part of the stellar parameter space for life. Its spectral type, G-type, what astronomers call a yellow dwarf, though it appears white from space, represents about 7% of stars in the Milky Way. There are more red dwarf stars, called M-type stars, which are dimmer and longer lived, but their habitable zones are close enough to the star that tidal locking and flaring activity present significant challenges. Whether life could survive and thrive on a tidally locked planet is one of the most actively debated questions in exoplanet habitability research. What we know about the Sun's specific energy output is also tied to the molecules that life uses. The wavelengths of light that the Sun produces most intensely the visible range, roughly between 400 and 700 nanometers, are the same wavelengths that chlorophyll in plants is most effective at absorbing. This is not a coincidence of design. It is the result of billions of years of evolution. Photosynthetic organisms evolved to capture the most abundant wavelengths in the incoming solar spectrum. The peak sensitivity of the human eye, around 555 nanometers, in the green range, coincides almost exactly with the peak intensity of sunlight at Earth's surface. Our biology is tuned to this star. Remove this star, and you lose not just the energy source, you lose the evolutionary context in which every photosensitive, temperature-sensitive, seasonally responsive biological system on Earth was shaped. The circadian rhythm, the visual system, the photoperiodic responses of plants that govern flowering and dormancy, the vitamin D synthesis pathway, the hormonal response to light exposure. All of these are the evolutionary legacy of 4.5 billion years of life, adapting to the specific light output of a specific star. This is the deeper answer to the question of what would happen if the Sun went dark. It would not just deprive life of energy, it would break the fundamental environmental parameters to which life on Earth's surface has adapted over its entire evolutionary history. The question is whether the adaptations capable of surviving in the remaining energy landscapes, geothermal heat, chemical energy, nuclear energy, are sufficient to allow complex life to persist. The answer is yes, for some complex life. The tube worms at hydrothermal vents, the bacteria in the deep crust, the archaea in hot springs, these organisms are already living in that world. They already represent the alternative. They have been there the entire time, a parallel world of life that the Sun's dominance has simply overshadowed. There's a philosophical dimension here that bears brief consideration. Life on Earth as we typically think of it, the visible biosphere of plants, animals, fungi, and the microbial communities we readily observe, is what could be called the solar biosphere. It runs on sunlight. It is the product of photosynthesis, scaled up through billions of years of ecological and evolutionary history. But beneath it, there is what might be called the geochemical biosphere. Slower, darker, colder in some places, and hotter in others, dependent on chemistry rather than light, extending into the deep rock and the deep ocean. It is less visible. It is less studied. It is arguably less dramatic in the short term. But in terms of total biomass estimates, some researchers have suggested it may rival or even exceed the solar biosphere. If you had asked a biologist in 1970 to estimate the total biomass of life on Earth, they would have given an answer dominated by plants, followed by bacteria in soils and oceans, with animals and fungi trailing. The concept of a deep geochemical biosphere essentially didn't exist. It was not in the textbooks, it was not in the models. It has only become clear through decades of deep drilling projects, ocean sampling, and the systematic study of extreme environments that the biosphere extends far deeper and far more widely than anyone imagined. The estimate published by the Deep Carbon Observatory in 2019 suggested that subsurface life, everything living below roughly 4 meters in depth, comprises somewhere between 15 and 23 billion metric tons of carbon, compared to roughly 500 billion metric tons of carbon in surface plant life. The subsurface estimate is uncertain by a large factor. Measuring life deep in the crust is technically very difficult, but the point is that the number is significant and not negligible. There is a lot of life that never sees the sunday. This science is young. The oldest deep borehole projects date to the 1970s and 80s. The systematic sampling of deep ocean sediments for biological activity has accelerated only in the past 2 decades. The recognition that organisms can survive and remain metabolically active at temperatures above 100 degrees Celsius and under pressures of hundreds of atmospheres is still recent enough to seem remarkable. The discovery of extremophiles organisms living at the extremes of temperature, pressure, radiation, and chemistry has fundamentally changed astrobiology. Before the discovery of organisms living at 222 degrees Celsius in hydrothermal vents, the assumption was that life required temperatures between roughly 0 and 60 degrees Celsius. That assumption has been replaced by a much wider understanding of the physical range within which life can operate. Hyperthermophiles, the most extreme heat-tolerant organisms, metabolize sulfur, iron, hydrogen, and other inorganic compounds at temperatures that would instantly denature the proteins of most organisms. Their proteins are stabilized by different molecular mechanisms: more hydrophobic cores, more disulfide bridges, salt bridges between charged amino acids. Evolution, given enough time and selective pressure, can adapt the basic biochemistry of life to conditions that seem impossibly extreme from a room temperature perspective. Psychrophiles live at the other extreme temperatures, close to and even slightly below 0 degrees Celsius, in the brine channels of sea ice, in supercooled groundwater, in the dry valleys of Antarctica. They produce antifreeze proteins and modify their membrane compositions to maintain fluidity at low temperatures. They have solved, at the molecular level, the problem of staying alive when everything around them is freezing. Piezophiles survive under extreme pressure, the creatures of the deep ocean, living at pressures of 500 to 1,000 atmospheres in the Mariana Trench and other deep-sea trenches. Their enzyme systems are adapted to function at pressures that would crush most proteins. Radio-resistant organisms, like Deinococcus radiodurans, can withstand radiation doses that would be lethal to a human at a factor of 1,000. They have evolved extraordinarily efficient DNA repair systems that can reassemble a shattered genome within hours. Each of these extremophiles represents a possible model for life in environments elsewhere in the universe. And each of them expands our understanding of what life requires, which turns out, repeatedly, to be less than we assumed. None of them require the Sunday. This is the thread that runs through all of it. The sun is where Earth's most visible, most complex, most ecologically dominant life gets its energy. But it is not where all life gets its energy. And in the thought experiment of sudden darkness, it is the non-solar life, the deep bacteria, the vent ecosystems, the subsurface archaea that inherits the Earth. The surface of the planet, the thin solar-powered film that includes every forest, every farm, every city, every species you could name from memory, goes dark and cold. The deep world carries on. The Earth itself, old and still hot inside, doesn't notice much, not for millennia. In the end, perhaps the most honest answer to the thought experiment is this: the sun going dark would be the end of the world as humans experience it, and the beginning of a world that has always existed just beneath our feet. The question of which world is more fundamental, which is the baseline, and which is the special case, is one that extremophile biology, astrobiology, and the systematic exploration of Earth's deep interior have been quietly rewriting for the past half-century. The answer, they suggest, is not what you might expect. The deep, dark, geochemical world is older, more widespread, and more resilient. The bright, warm, solar world, the one we live in, is the remarkable exception, the special case. The thin, radiant, temporary overlay on a planet that has its own internal story. That story continues regardless of what the star at the center of our solar system does. Earth's heat will last for billions of years after the sun becomes a white dwarf. The deep ecosystems will outlast the surface ones. And wherever in the universe, the same conditions hold a rocky body with liquid water, chemical energy, and enough time, the same story may be playing out right now, in the dark, far from any star. We just haven't found it yet. Let's step back and ask the question more carefully, because there's a layer of the story we haven't fully examined. The physics of why stars produce light at all, and what it would actually mean, physically, for a star to stop. Stars are pressure balanced against gravity. That's the essence of stellar structure. The Sun's gravity, generated by its enormous mass, roughly 2 × 10⁻30 kilograms, or about 330,000 times the mass of Earth, tries to collapse the entire structure inward. Opposing that collapse is the pressure produced by the hot plasma at the core, where temperatures reach about 15 million degrees Celsius. At those temperatures and densities, atomic nuclei have enough kinetic energy to overcome the electrostatic repulsion that normally keeps protons apart, allowing them to fuse. This balance between gravity and pressure is called hydrostatic equilibrium. It is not a fragile balance. If the core temperature rises, the pressure increases. The star expands slightly, which lowers the density and temperature in the fusion zone, which slows the fusion reaction, which lowers the temperature, which allows gravity to compress the star again. It is a self-regulating system, a thermostat of nuclear physics. This is why the Sun has been shining at roughly constant luminosity for 4.5 billion years, without exploding or collapsing. It automatically adjusts. The only way to turn off a star is to remove this balance. Either remove the fuel and let the hydrogen run out, or somehow remove the pressure quickly enough that gravity wins. The former takes billions of years for a star like the Sunday. The latter would require a catastrophic external event that doesn't have a plausible mechanism in normal stellar physics. But there's another way to think about it. Even if somehow the fusion reaction stopped, even if you could flip a switch and halt every nuclear reaction in the Sun's core, the Sun would not immediately go dark. The energy stored in the Sun's plasma would take an extraordinarily long time to radiate away. This brings up one of the most counterintuitive facts about the Sun. The light we see today was not produced in the core moments ago. It was produced roughly 100,000 to 170,000 years ago. The Sun's interior is so dense that photons produced by fusion in the core undergo an immense number of scattering events before they reach the surface, slowly random walking outward. The process is called a random walk in a dense medium, and the time it takes is determined by the mean free path of photons in the solar plasma, roughly 1 centimeter per collision, and roughly 10 to the 26 collisions to escape. After this geological timescale journey through the radiative and convective zones of the Sun, photons finally reach the photosphere, the thin, relatively transparent outer layer, and escape into space. The light you see from the Sun right now originated in nuclear reactions that happened when modern humans were just beginning to settle into the first large communities of the late Paleolithic. The photons that will reach Earth 100,000 years from now are being produced by fusion reactions happening in the Sun's core as you read these words. So, in an extreme hypothetical, the Sun's fusion stops right now. It would take roughly 100,000 years before the Sun began to noticeably dim. The vast reservoir of thermal energy stored in the solar plasma would continue radiating. Observers on Earth wouldn't see any change for longer than the entire span of recorded human civilization. This is not a practical aspect of the thought experiment. It is a physical reality that reframes the relationship between nuclear fusion and light output. They are separated by 100,000-year time lag. The Sun we see is the afterglow of reactions that happened before Homo sapiens had reached every continent. The photons' journey from core to surface is not their only interesting property. The spectrum of light that leaves the Sun's photosphere is not a pure blackbody spectrum. It has absorption lines called Fraunhofer lines, where specific wavelengths are absorbed by different elements in the Sun's atmosphere. These lines were first catalogued systematically by Joseph von Fraunhofer, a German optician in the early 19th century. He identified over 500 dark lines in the solar spectrum. Later, physicists realized that each of these dark lines corresponded to the absorption wavelength of a specific element. Hydrogen absorbs at specific wavelengths in the Balmer series. Sodium absorbs at roughly 589 nanometers in the yellow-orange range. Calcium has strong absorption lines in the violet. By reading the pattern of dark lines in the solar spectrum, chemists and physicists in the 19th century were able to determine the elemental composition of the Sun without ever going there. This technique, spectroscopy, became the foundation of astrophysics. It's how we know the composition of every star we've ever observed. It's how we know the atmospheres of exoplanets contain specific molecules. It's how we will look for biosignatures, the spectral fingerprints of biological processes on distant worlds. The Sun's spectrum tells us that it is composed primarily of hydrogen, roughly 73% by mass, with helium at about 25%, and all other elements together making up about 2%. This 2%, the metals in astronomical terminology, meaning every element heavier than hydrogen and helium, is what makes the solar system interesting from a habitability perspective. The heavy elements in Earth, in the ocean, in our bodies, the carbon, oxygen, nitrogen, silicon, iron, calcium, were produced in older generations of stars that lived and died before the solar system formed. The Sun inherited their ash. This connection between stellar generations is one of the most profound findings of 20th century astrophysics. We are made of stardust in a literal, physical sense. The iron in your hemoglobin was produced in a supernova explosion billions of years ago. The calcium in your bones was forged in the cores of stars that no longer exist. The oxygen you breathe was produced partly by early stars and partly by the photosynthetic activity of Earth's own biosphere over billions of years. The Sun, the star at the center of this thought experiment, is itself a third-generation star formed from material that has been through at least 2 previous stellar cycles. Its composition reflects billions of years of nucleosynthesis by generations of stars that predated it. When the Sun eventually becomes a white dwarf and cools over billions of years, it will represent one more stellar corpse, contributing its mass to the eventual formation of new stars, new planets, and perhaps new biospheres. The cycle continues. Nothing is wasted. The elements the Sun fuses from hydrogen into helium, and the heavier elements the helium might eventually become in the red giant phase, all of it goes back into the interstellar medium, available for the next generation. This galactic recycling is why the universe is progressively more metal-rich over time. The first generation of stars, the population 3 stars that formed within a few 100 million years of the Big Bang, contained only hydrogen and helium, the elements produced in the Big Bang itself. They produced heavier elements through fusion and distributed them in supernova explosions. The second generation of stars, population 2, was richer in heavy elements. Our Sun and its contemporaries, population 1 stars, contain the most diverse elemental composition of any stellar generation. The trend continues. Stars forming today in stellar nurseries throughout the Milky Way are forming from gas clouds that are richer in heavy elements than the cloud from which the Sun formed 4.5 billion years ago. The planets forming around those new stars will be more diverse in their chemistry than Earth was when it formed. Whether that makes them more or less habitable is a question that habitability researchers are still working through. More heavy elements means more material to build terrestrial planets, more radiogenic heat to drive geology, and potentially more complex surface chemistry. It also potentially means more toxic heavy metals in biologically available forms. The universe is changing as it ages, and the Sun sits in a specific position in that timeline, young enough to have inherited the chemical richness of multiple stellar generations, old enough to have provided a stable, continuous energy source for the evolution of complex life. Remove the sun from this picture, and you're not just removing an energy source, you're removing the entire context in which Earth's specific biosphere evolved. The cold, dark Earth that remains is geologically the same planet. Physically, it retains its mass. Its orbit would scatter. Its atmosphere would gradually freeze and settle. But its rock, its internal heat, its deep ocean chemistry, these persist. What doesn't persist is the particular experiment in solar-powered biology that has been running on Earth's surface for 3.5 billion years. That experiment ends. But experiments end all the time. The Permian biosphere ended. The Cretaceous biosphere ended. Something new followed each time. The post-solar Earth, in the long view, would be a different kind of stage for a different kind of experiment. Slower, darker, chemically driven rather than photochemically driven, but not lifeless. The organisms that would be the inheritors of that world are not dramatic. They are invisible to the naked eye. They have no names most people know. They produce no oxygen, build no forests, and construct no civilizations. But they have been on Earth longer than any of the organisms we'd think of as characteristic of life here. They were here before plants, they were here before animals, they were here before the Cambrian explosion. They weathered every mass extinction. In the thought experiment's dark aftermath, they would be there still. Researchers studying the deep biosphere have described the organisms living kilometers below the surface as effectively isolated from the surface world for millions to hundreds of millions of years. They are, in a sense, evolutionary experiments already underway in the absence of sunlight. Their evolution has been proceeding in their deep rock environments, driven by the selective pressures of heat, pressure, chemical gradients, and radiation from radioactive decay, completely uncoupled from the solar-powered world above. Some of them have been growing so slowly that the concept of a generation time doesn't quite apply in any familiar sense. A bacterium that divides once every 1,000 years is, metabolically, almost in suspended animation compared to the bacteria in your gut that divide every 20 minutes. But it is not dead. It is not dormant. It is alive, metabolizing, repairing DNA damage from background radiation, adapting by mutation and natural selection, just at a pace calibrated to the trickle of chemical energy available in its environment. If you made an evolutionary film of the deep biosphere over 1 billion years, playing it back at normal speed, you would see it as motionless, but it is not. It is the slowest version of the same story that the surface biosphere tells faster in brighter colors, powered by a different star. The sun going dark ends the fast, bright, solar version of that story. The slow, dark, geochemical version continues. And it will continue if our best physics is right, for as long as Earth's interior remains warm enough to drive the reactions that feed it. That may be a very long time indeed. Earth's internal heat is declining, but slowly. The half-lives of the primary heat-producing radioactive isotopes range from 700 million years for uranium-235 to 14 billion years for uranium-238. The total geothermal heat output of Earth has been declining since Earth's formation, but slowly enough that the heat flux 4 billion years from now will still be a substantial fraction of what it is today. The deep biosphere has a long future, even after the sun is gone. This is the unexpected conclusion of the thought experiment. We started by imagining the end of the sun and the darkness that would follow. We arrive at the recognition that Earth itself is a long-term energy source, that life adapted to that energy source already exists, and that the surface world, for all its richness and complexity, is the temporary layer. The deep world is the permanent foundation. The sun is 8 light minutes away. It has been driving life on this planet's surface for 3.5 billion years. It will keep doing so for another billion or more before the warming becomes too severe for complex surface life. In 5 billion years, it will expand to a red giant and transform the inner solar system. In 6 billion years, it will collapse to a white dwarf. Through all of this, the deep Earth keeps its own counsel. It doesn't need the Sunday, it never did. And that, perhaps, is the most important thing the thought experiment reveals. Not what we would lose in the dark, but what would remain. There's one dimension of this thought experiment that tends to get passed over, and it might be the most human part of the whole story. What would actually happen to civilization in the social and psychological sense, not just in the thermodynamic sense? The physical consequences of solar darkness are tractable to model. Temperature curves can be estimated. Crop failures can be predicted. Power grid failures can be mapped. But the response of 8 billion people to an event with no precedent in human experience, no cultural framework, no religious or mythological template that precisely covers it, that is harder to model and in some ways more consequential in the near term. In the first hours, no one would understand what had happened, not because information would be unavailable, but because the scale of the event would be cognitively overwhelming. The human brain processes sudden, extreme changes to familiar environments with a predictable sequence. Orienting response, alarm, search for familiar patterns, attempt to fit the experience into existing categories. None of those categories would apply. The sun doesn't go out. It doesn't even flicker. In every cultural tradition on Earth, the sun is the one invariable. Its daily return is the oldest promise nature makes to human life. The sociological literature on responses to large-scale disasters, earthquakes, tsunamis, nuclear accidents, consistently shows that the immediate response of most people is not panic. It is what researchers call the milling process. Standing around, talking to neighbors, trying to gather information, attempting to establish whether the event is real and how serious it is. Panic, in the Hollywood sense, is actually quite rare in disaster scenarios. What is far more common is stunned inaction, followed by the gradual mobilization of social structures. Those social structures, in the sun-dark scenario, would face a challenge unlike any before. Normal disasters have a geographic boundary. If your city is destroyed by an earthquake, the surrounding regions are intact and can provide aid. Institutions and governments remain in place. Communication networks link affected areas to unaffected ones. The sun-dark scenario has no geographic boundary and no external aid structure. Every institution, government, communication network, and supply chain in the world would be operating under the same simultaneous shock. What would help? The evidence from historical cases of simultaneous multinational stress, the 2 world wars, the 1918 influenza pandemic, the 1930 Great Depression is mixed. Those events strained social cohesion. They also, in some cases and regions, produced remarkable collective mobilization. Humans are a social species that evolved in conditions of intermittent catastrophe. The capacity for coordinated group response to severe threat is not a cultural invention. It is a biological inheritance. In the sun-dark scenario, the communities best positioned to organize effective responses in the first days would likely not be the wealthiest or most powerful. They would be the ones with the strongest existing social cohesion, the clearest communication, and the most relevant practical skills. Small, tight-knit communities with experience managing difficult environments, farming communities, indigenous communities in harsh climates, communities in regions already accustomed to seasonal darkness and cold might organize faster and more effectively than large, atomized urban populations. The enormous cities of the 21st century places, like Tokyo, with roughly 37 million people in the greater metropolitan area, or Shanghai, Mumbai, Cairo, Lagos would face cascading failures with extraordinary rapidity. Urban food supply chains have essentially no slack. Most large cities have food stocks sufficient for a few days to a couple of weeks at normal consumption rates. Without resupply, and without functioning agricultural production in the surrounding regions, urban populations would face food shortages within weeks. The movement of large populations toward geothermal zones and surviving agricultural areas, if it happened, would be organized chaos at best. The logistical challenge of moving hundreds of millions of people across frozen landscapes, with failing transportation infrastructure and without a functioning global supply chain, is essentially unprecedented. The closest historical analogue might be the great migrations and population movements of the early medieval period, following the collapse of Rome. But those happened over centuries, not weeks, and in a warming rather than cooling world. Historical precedents for rapid, large-scale population movement under crisis conditions are not encouraging. The Dust Bowl migration of roughly 350,000 people from the Oklahoma Panhandle region to California in the 1930s, depicted in John Steinbeck's novel The Grapes of Wrath, involved a tiny fraction of the population movements that would be required and produced immense human suffering even with functioning national infrastructure. The partition of India and Pakistan in 1947, which moved roughly 15 million people in a few months, was one of the largest mass migrations in history and was accompanied by enormous violence and death, even in a temperate climate with functioning railways. Scale either of those up by a factor of thousands, add plummeting temperatures, failing energy infrastructure, and universal resource scarcity, and the challenge becomes clear. Not impossible, but staggeringly difficult. The institutions that would matter most in such a scenario are the ones that currently receive the least attention in popular discourse about existential risk. Local food storage systems, distributed energy generation, community-level social capital, and the practical knowledge of survival in cold and dark conditions. The countries with the highest scores on international indices of social trust, consistently the Nordic countries, Iceland, and a few other small, cohesive nations would likely perform better, not because of their wealth or military power, but because of their capacity for organized collective action. This is the lesson that social scientists who study large-scale disasters have articulated repeatedly. The response to catastrophe is determined more by social structure than by technological capacity. A well-organized, mutually trusting community with modest resources will outperform a wealthy, atomized one. The technical tools for survival in a sun-dark world largely exist. The social tools for distributing them equitably and organizing their use at scale, those are the actual constraint. The food system problem deserves specific attention because it would be the single most immediate threat to human life after the temperature drop. Modern agricultural civilization feeds 8 billion people through a system that has essentially no buffer. Global grain stocks at any given time represent roughly 3 to 4 months of global consumption. Livestock populations depend entirely on ongoing grain and forage production. Seafood production from surface waters would collapse as ocean surface temperatures dropped and ice spread. The food system's dependence on solar energy is total. Photosynthesis is the entry point for essentially all food energy in the global diet. The alternatives chemosynthetic bacteria, underground fungi, food produced under artificial lighting exist but are entirely insufficient to replace global photosynthetic food production at any near-term scale. What would be available? Stored food grains, legumes, preserved foods for a few months. Livestock, which represent stored biological energy, but consuming livestock consumes the animal rather than its ongoing production, so herds would be depleted rapidly. Marine resources from the deep ocean, which would remain productive for longer than surface fisheries. And the wild card, underground food production. Mushrooms and certain fungi can grow in the dark. They don't photosynthesize, they decompose organic matter. Given enough organic material, dead plant matter, agricultural waste, organic material of any kind, they can produce edible fruiting bodies without any sunlight. Mushroom cultivation in mines and cellars is historically practiced. It is low-tech. It scales with available organic material. In the first months of solar darkness, mushroom cultivation in any space with organic substrate and controlled temperature could provide a meaningful food supplement. More sophisticated is the hydroponic and aeroponic production of food under LED lighting, powered by electricity. This is the technology that most serious thinking about long-term survival in solar darkness would depend on. It works today. The International Space Station grows leafy greens under LED lights. Commercial vertical farms operate in abandoned warehouses and repurposed industrial buildings in cities around the world. The technology is proven. The constraints are energy and scale. Current global vertical farm production is a negligible fraction of global food requirements. Scaling it up to even a few % of global caloric requirements would require decades of investment under normal conditions. Under catastrophe conditions, with scrambled supply chains and failing infrastructure, the pace of scaling would be limited by what could be repurposed and redirected from existing capacity. The realistic picture of food survival in the solar darkness scenario is a patchwork. Existing food stocks providing a bridge, mushroom cultivation providing a supplement, vertical farming at surviving powered facilities providing a small but growing contribution, and deep ocean fisheries providing protein for coastal communities for longer than surface fisheries. None of this is comfortable. None of it feeds 8 billion people. But it is not nothing. It is the difference between total extinction and the survival of a remnant. The question of who constitutes that remnant, which communities, which regions, which institutions, is one that most people find uncomfortable to think about, because the honest analysis suggests it would be determined by a combination of geographic luck, existing infrastructure, social cohesion, and political organization. The geologically fortunate communities near active volcanic zones would have advantages that have nothing to do with virtue or preparedness. The socially cohesive communities would have advantages that have everything to do with decades of investment in social capital. Researchers in the catastrophic risk field have argued that this analysis has a direct policy implication. The best preparation for low probability, high consequence global catastrophes is not bunkers or escape plans for elites. It is broad investment in distributed food security, community resilience, social trust, and the equitable distribution of knowledge and skills for surviving under extreme conditions. A world in which 8 billion people have reasonable food security and strong community bonds is far more resilient to catastrophe than a world in which a small number of extremely well-prepared individuals have bunkers and the rest have nothing. This is a finding that crosses the boundary between thought experiment and practical policy recommendation. And it's one that the solar darkness thought experiment makes unusually clear, precisely because the event is so total and so simultaneous that there is no external rescuer, no unaffected region that can provide aid, no cavalry coming. In that scenario, the only resources available are the ones already present in communities and ecosystems. The communities that have invested in those resources in each other, in local food systems, in shared knowledge and infrastructure, are the ones that persist. The sun will not go dark, but the lessons of imagining that it might are not wasted. They point toward the foundations that matter, the investments that pay off in the scenarios that can actually happen, and the recognition that the resilience of civilization is built in the ordinary work of ordinary times, not assembled in a crisis. These are the stakes of the thought experiment, not the drama of sudden darkness, but the clarity it provides about what we actually depend on and what we might actually need to protect. 5 billion years from now, when the sun begins its long expansion toward a red giant, Earth's surface will be long uninhabitable by anything like complex life. The ocean will have evaporated. The rocks will be glowing. Whatever evolution has done in the deep crust and the deep ocean over those billions of years will be overprinted by heat beyond anything the surface biosphere ever experienced. But between now and then, there are 1 billion years or more of surface habitability remaining, assuming we don't make irreversible changes to the conditions that sustain it. That is a number so large, it is effectively meaningless to human experience. 1 billion years ago, the most complex life on Earth was simple, multicellular organisms barely visible to the naked eye. Everything from the Cambrian explosion to the present happened in about 530 million years. What could happen in 1 billion more years if the solar-powered experiment on Earth's surface continues, if intelligence and complexity and intentionality keep compounding, is genuinely beyond imagination. The possibility space is too large. And yet here we are, 8 billion people on a warm, photosynthetically active, ocean-covered world in the middle of the sun's long, stable middle age, asking what would happen if the light went out. The answer that the physics gives back is not entirely comforting and not entirely hopeless. It is honest. Some of what we depend on is fragile. Some of it is not. The deep world endures. The fast surface world is remarkable and temporary, and the capacity to understand all of this, to model it, analyze it, reason about it, and ask what we should do in its light. That is perhaps the most interesting thing that has happened on this planet in its entire 4.5 billion year history. We don't know what happens next. The questions that remain, whether life exists elsewhere in the universe, whether complex civilization is common or rare in the galaxy, whether the deep geochemical world harbors microbial life in hundreds of billions of solar systems, are genuinely open. The instruments being built today and the missions being launched this decade are designed to answer some of them. The sun shines, for now, for long enough. And the questions it raises, by its presence and by its imagined absence, are worth taking seriously. There's one last thread worth pulling on, because it connects everything we've discussed to something currently unresolved in astrophysics. We've talked about the sun as if it's exceptional, as if its specific combination of mass, age, stability, and spectral output represents a kind of fine-tuning that makes life possible here. In one sense, that's clearly true. Earth's biosphere is exquisitely calibrated to this particular star. But how exceptional is this combination in the broader context of the galaxy? The answer, as of the mid-2020s, is that we genuinely don't know how special it is. The Kepler Space Telescope, which operated from 2009 to 2018, surveyed over 150,000 stars and found thousands of exoplanet candidates. The data revealed that planets are extraordinarily common. The galaxy appears to have more planets than stars. Many of those planets are Earth-sized. A substantial fraction of them orbit in the habitable zones of their host, stars the region where liquid water could exist on the surface. But habitable zone membership doesn't mean habitability. Mars is in the outer habitable zone of the Sunday. Venus was in the inner habitable zone for perhaps 2 billion years before runaway greenhouse warming transformed it. Habitability depends on a complex interplay of factors: planetary mass, which determines whether a planet can retain an atmosphere; geological activity, which regulates the carbon cycle and recycles nutrients; axial tilt, which determines seasonal variation; the presence of a large moon, which stabilizes the axial tilt over long timescales; and the specific stellar activity of the host star. The Sun is unusually quiet for its stellar type. Solar flares and coronal mass ejections, massive eruptions of plasma and magnetic field from the Sun's surface do occur, and historical events like the Carrington event of 1859 demonstrate they can be powerful enough to disable electrical infrastructure. But compared to many other stars of similar mass and age, the Sun's flare activity is modest. Stars of the same spectral type can vary significantly in their activity levels, and a more active sun would produce more ultraviolet radiation and higher energy particles reaching Earth's surface, potentially posing serious challenges for surface life. The question of whether life is common or rare in the universe, the Fermi paradox, named after physicist Enrico Fermi's famous question of where all the extraterrestrial civilizations are, remains one of the most consequential unanswered questions in science. The thought experiment about a dark sun is, in a sense, one data point in thinking about that question. It tells us that even a planet which loses its star is not necessarily sterilized. Life persists in the deep. The geochemical world carries on. If that's true for Earth, it may be true for many worlds. The galaxy could be full of frozen, starless rogue planets, harboring microbial life in warm subsurface oceans, powered by radioactive decay, invisible to any survey that looks for planets in stellar habitable zones, because they aren't orbiting any star at all. They are simply drifting through the interstellar medium, dark and cold on the surface, warm and alive in their depths, unknown and unknowable, until a telescope sensitive enough to detect the faint thermal signature of a warm ocean beneath kilometers of ice happens to look in the right direction. We are in the early stages of having telescopes that might, in principle, detect such objects. Not easily, not soon, but the trajectory of the technology points in that direction. The Nancy Grace Roman Space Telescope, designed to detect gravitational microlensing events with far greater sensitivity than previous surveys, may reveal the true population of Earth-mass free-floating planets. Future space-based infrared observatories could, in principle, detect the thermal emissions of warm-bodied rogue planets. The science is ahead of the technology, but the technology is catching up. This is what the thought experiment about the dark sun ultimately connects to: the frontier questions in astrobiology and planetary science that are being actively investigated. The deep life that inherits the Earth in the thought experiment is the model for what researchers are looking for in subsurface oceans across the solar system, and in the population of rogue planets drifting through the galaxy. The physics that keeps deep Earth life warm without sunlight is the physics that might keep alien life warm in the dark between stars. Every question is connected to the next. The sun goes dark, the surface freezes, the deep world persists. The conditions for that persistence are not special to Earth. The galaxy is full of bodies with internal heat, liquid water, and chemical energy. Whether any of them have life is a question we are, for the first time in the entire history of intelligent creatures on this planet, equipped to begin answering. That answer is still being found. The sun, in the end, is a question that answers itself by shining. It poses no puzzle because its presence is the default condition. Only in imagining its absence do we see clearly what it actually does and what exists without it. That clarity about the architecture of dependence, about where the foundations actually are, about what endures when the dominant energy source disappears, is not available to us in ordinary circumstances. We live in the light and take it for granted. We build systems that assume the solar input will continue, and those systems work because the input does continue. The assumption is valid. The convenience is real. The stability of the sun over any human timescale is not an illusion, but understanding what would happen if it stopped is one of the most revealing exercises in systems thinking available to science. It shows us the full structure of the living world, from the solar film at the top to the geochemical foundation below. It shows us the limits of our technology and the latent strengths of our biology. It shows us that the question of what life needs, stated at its most fundamental level, is still being answered by researchers drilling into the crust, by spacecraft studying ocean moons, by telescopes surveying the cold, dark, vast space between the stars. That is where we are. That is what the darkness shows us.